Currently we're discussing alkenes, their synthesis and their reactions, and previously we talked about a reaction roadmap where we said that if we take all the possible ingredients or functional groups or starting materials and the reactions that give us alkenes, and we take all the possible reactions that alkenes can go through to give us different products, and we put these together, we get what we can call a reaction roadmap, which is essentially just a combination of all the different reactions that a functional group is made from, can possibly be made from, and all the different products that a functional group can lead to through the various reagents and reactions. An understanding of such a reaction roadmap, in my opinion, is really important for to be successful on your exams or in any organic chemistry course. Most test questions there's a lot of different types of test questions, two of which are you'll be given a reactant and a reagent, and you have to predict the right product. On the other hand, sometimes you will be given a product and you have to answer how to make that. Choose the conditions, the starting materials, and the reagents to make that. From here to here, this part is what represents the synthesis part of a roadmap, and from here to here represents the reactions that a functional group can go through. Currently, we're up to this part. We're just discussing, we're learning the reactions that can give us alkenes. We're just doing this part of the reaction roadmap, and then we're going to learn reactions of alkenes. One of the reactions that we learned already of the alkyl halides in the previous chapter was an elimination reaction, which is a reaction that can give us alkenes. We learned that an alkyl halide which has a halogen bonded to an sp3 carbon, and a minimum of 2 carbons are required for a molecule in alkyl halide to go through elimination, because a double bond can form between 2 carbon bonds. So an alkyl halide, which is a halogen bonded to an sp3 hybridized carbon, in the presence of a base, gives us an alkene. The base attacks a hydrogen adjacent to the carbon bearing the X. So if this is the carbon bearing the X, and which we can call the alpha carbon, then all the carbons directly adjacent to that carbon are called the beta carbons. And there could be more than one beta carbon. There could be multiple beta carbons. In this case, just to keep it simple, for simplicity's sake, not to make it crowded, I'm starting off with an example which has only one beta carbon. So the beta carbon, meaning the carbon adjacent to the carbon bearing the X, the base abstracts a proton from the beta carbon, which is the carbon adjacent to the carbon bearing the X. The base removes the proton. Proton does not take any electrons from the molecule with it. The CH bond, the electrons from the CH bond move between the 2 carbons, make a pi bond there. The CX bond is broken heterolytically. The leaving group leaves with the electrons in the CX bond. As a result, we get a pi bond which has been created from the CH bond density, and we get the base bonded to the H plus the leaving group. And I think it's really important for us to remember where the bonds are breaking, where the bonds are forming, where the electrons are moving, basically. So the BH bond electrons are provided by the base. The CH bond moves, the CH bond of the carbon's bond to the hydrogen that's abstracted, that those electrons move as this pi electrons between the two carbons, and the leaving group leaves with the CX bond. Now, a more detailed discussion of this has been done before. You can rewatch that. We can discuss that again if you need to review that. But over here, we're just talking about, we're in the synthesis part of the reaction of the of alkenes, and we're discussing how to make alkenes, and we're just reviewing elimination based on that. So as you'll soon see, this is only one kind of an elimination, and the reason I highlighted the bond movements, electron movements, it's important to keep that in mind, because this is only, you'll soon see that's only one kind of an elimination. There are many more molecules, many more substrates. In this case, the substrate is an alkyl halide, but we'll soon see that many more substrates are capable of going through elimination with different leaving groups attached. And the difference will be here, the groups that are removed will be different, but many different substrates can go through elimination when they react with bases to give us alkenes. So those reactions will be very similar, they'll have very similar patterns, and that's why an understanding of this is so important, because then you can just reapply the same knowledge to a lot of different reactions when you see these patterns. That's why it's important to know this. Whether that's E1 or E2 is a different story based on the reaction order. So this is only one kind of an elimination, and specifically we call this dehydrohalogenation. Because it's a removal of a hydrogen and a halogen. So, and hence the name dehydrohalogenation. That's just one kind of an elimination reaction, and there are many other kinds of elimination reactions, which we'll soon see. Now we need to focus on how to make alkenes. In the previous chapter, we were given different substrates, and we were able to predict what kind of a product will be made, what kind of an alkene specifically will be made. But now we want to start thinking backwards, where we are given an alkene, and we need to think backwards and decide on what conditions to go with that are going to give us that alkene in the highest yield possible. So we already reviewed all the different conditions that favor E2, and here I would like to give you a minute to list those conditions. So we're going to label this conditions that favor E2, and because this has been discussed before, conditions that favor alkene formation. The reason we need to know these is because the same alkyl halide that we just mentioned, which has an X attached to an sp3 carbon, is also just as likely usually to go through a substitution. Most bases generally are also good nucleophiles, and alkyl halides are equally capable of going through substitution in general. So the same product given a good nucleophile, when treated with a good nucleophile, can give us a product which depends on the choice of nucleophile, where all that happens is that the nucleophile has been replaced by the X. And then the same reactant given a base can give us an alkene. So when we want an alkene to form, and when we're doing synthesis questions, if this is your desired product, you want to avoid the other. You don't want this reaction, this molecule, to go through the substrate, to go through substitution, if you're trying to do a synthesis question that involves making an alkene. So that's why we're talking about conditions, because SN substitution and elimination are usually competing reactions, we're trying to learn ways that we can prevent substitution from happening and favor elimination. And one of the things we need to consider is, well, elimination, should we do E1 or E2? Is one better? And the answer is yes. And we said E2 is better. And the reason for that is E1 has more competition, E1 has more competing reactions. The next thing we talked about was how the choice of substrate, does the choice of substrate affects, can we choose a substrate to favor elimination? And the answer is yes. We already decided between E1 and E2. E2 is better. Well, E2 competes with E1, with SN1. Sorry, E2 competes with SN2. So E2 and SN2 are competing reactions, while E1 and SN1 are competing reactions. So right now, since we're trying to make it go through E2, we need to find a way to avoid SN2, or to not let SN2 happen. And the way we do that is we choose a substrate that's poor for SN2. And it just happens to be that the poorest substrate for SN2, which are tertiary substrates, are also the best for E2. So the second thing we should keep in mind when doing synthesis questions making alkenes is to keep in mind that tertiary substrates, when possible, are best, because they're poorest for SN2. They're the least suitable for SN2 reactions, which is what we're trying to not let happen. And the third thing that we talked about was the choice of base. We tend to try to choose a strong, bulky base. If the base is strong, it's going to force second order elimination, meaning it's all going to be concerted. It's going to prevent E1. It's going to force E2. If it's bulky, so strong favors E2. If the base is bulky bases, remember, and you can see my previous discussion on this, a separate discussion on nucleophiles versus bases, nucleophilicity versus basicity. But generally, most bases are good nucleophiles, except when a base is bulky. Bulkiness or static hindrance does not affect basicity, but it affects nucleophiles. So bulky bases are still good bases, but they're poor nucleophiles, and that's why we choose them for elimination reactions, because they're not good for substitution. That's why we choose bulky. And something that I want to add to this from the previous clip is that when we choose a strong bulky base, that also is useful in making the anti-Zaitsev product, also useful. Which is also called the Hoffman product. And we'll talk about this in a bit. If you remember, in the previous chapter we learned the Zaitsev rule, or the Zaitsev product is the more substituted product. The Zaitsev rule tells us that when an alkene can give us more than one, when an alkyl halide or any substrate can give us more than one alkene, the most substituted alkene is the dominant product. It's the major product, Zaitsev rule. So for example, if we have a molecule if the X is, this looks like a tertiary alkyl halide, which is the best for E2. If we look at this substrate, we see that this is the alpha carbon. It has 1, 2, 3 beta carbons. So the double bond can actually form between these two carbons if one of these hydrogens is abstracted. Or the double bond could form between this carbon and this carbon if one of these hydrogens is removed, which will give us the same product. Or the double bond could form between this carbon and this carbon, one of these hydrogens is removed. If you see this, and let's try to do the product for each one. Well, if the double bond, and I would prefer to do the line structure for this. It's a 1, 2, 3, 4 carbon chain. And so far, we're saying the double bond could, this is the carbon bearing the Br. The double bond could form here, or the double bond could form there. And as we see, generally, the Zaitsev rule tells us that the more substituted alkene is preferred, so the double bond that's there will be preferred over the double bond that's there. But when you're doing a synthesis question and you come across an alkene that you want to make this, the use of a bulky base, so if we normally choose, let's say, a CH3 CH2OH, that's just CH2O minus, that's a toxide. That's a base, that's a non-bulky base that will favor, generally because the Zaitsev rule applies most of the time, that will, in that case, this will be the major product. But if we choose third butoxide, for example, it's a strong bulky base, and that favors the Hofmann product. So that's the Zaitsev product, and that's the Hofmann product. So in synthesis questions, when you want to make an alkene that is the least the product that is the least substituted alkene, then that can be accomplished by using a bulky base. So choosing a bulky base in alkene synthesis has two functions. One, it can be used to prevent substitution from happening because bulky bases are not good nucleophiles. And second, when a base attacks a proton, if it's bulky, it prefers to remove the proton in such a way that leads to the formation of the least substituted alkene. Please ask me questions if you have questions about this, if this is not clear. This is a point that I wanted to add from before. From a discussion, and we mentioned the different reasons we use the different features that the different features that we can choose to make of a reaction that we can choose to make elimination the more favorable reaction. And then we mentioned bulky bases, and I want to add this point to that the choice of a bulky base also leads to the formation of a Hofmann product, the least substituted alkene.